Okay, so today we're going to be going over 8.3 wave characteristics as well as 8.4. So 8.3 can be found on 385 to 387. So as you can see, it's a very short chapter. It just goes over some wave characteristics and terminology of a wave, basically. Okay, so today we're basically going to be going over waves in terms of their size, their shape, and the speed of which that they move. Okay, so very geometric features, basically. Okay, so we're going to talk about amplitude, wavelength today, phase, and phase shift. Okay, so here we have a wave, and this wave consists of a rope. Okay, and you have some parts that are labeled here. Okay, so the amplitude we define as, and we talked about this yesterday, but it's defined as the maximum displacement of a vibrating particle in a wave from its equilibrium point. So the equilibrium point in this case would be labeled as E. Okay, so E is the equilibrium point, and it's shown by this dotted line here. Okay, so you can see that if we measured from here to here, okay, B, that would be considered an amplitude, okay? But if we also measured from here to here, that would also be considered an amplitude, okay? Now, the max point in a transverse wave, we call this a crest, okay? And then the minimum point we call the trough, okay? Now, you can see here that through one cycle, the wave travels through a trough, through a crest, and then back to the equilibrium point. So this would be considered a wavelength. Okay, so from this point here to this point here is one wavelength. And it's denoted by this Greek symbol lambda. Okay, so it's kind of like this. All right. So if you take a look here, okay, if we're starting from this point here and this point, and we're ending back at that point, that would be considered one wavelength. Okay, so that's wavelength. This would be, sorry. This one here is showing the trough. This one here is showing amplitude. And this one here is showing a crest. Okay. So you can see that here. So this wave is moving in the rightward direction. Okay. You can see that if we're starting from the top of this crest and moving to the other top of the crest, that's one wavelength. And again, you can do the same and move to this top here, and that you would get a second wavelength. So it looks like there are at least two complete wavelengths there. Okay. You can also see here, this would also be considered a wavelength if we're starting from the equilibrium point. Right? You have your two troughs, three troughs, right? You have your three crests. And if you were to measure the trough and the crest, that would be considered amplitude. We talked yesterday, about longitudinal waves and how they have regions of compression where air gets compressed and pressure increases for a period of time, very small period of time. And then the areas that have a decrease in air pressure we call rarefactions. And we know that the most common longitudinal waves are indeed sound. Okay, but here's an example of a longitudinal wave that would be a slinky. All right, so wavelength. Okay, so a continuous wave we know has many troughs, many crests that repeat one another, okay, or compressions and rarefactions. So the wavelength we define as the distance between two similar points in successive identical cycles of a wave, okay? So you can measure from crest to crest, you can measure from trough to trough, you can measure from equilibrium point to equilibrium point, but it has to cover one full cycle. Okay, so it's one full cycle. In the case of the longitudinal wave, it would go from compression to compression or rarefaction to rarefaction, as you can see here. Okay, or here. And that should be the symbol for wavelength. It's a bit blurry, but it is. Okay. So here it says sketch a periodic wave consisting of two complete wavelengths, each having a wavelength of 4 centimeters. Label the diagram with amplitude, crest, trough, wavelength, and equilibrium or rest position. So if we draw our equilibrium, okay, we can start here. There's one wavelength. There's two wavelengths, okay? So if we're measuring from here to here, right, that's one wavelength. Okay, and then if we measure from here to here, that's another wavelength, and it equals 4 centimeters in this case, right? We've got the crest, we've got the trough, and then we have the amplitude. Okay, so I think everyone should be pretty much okay with that. We're going to add some math to this now.
Sir?
Yeah.
How come like, on the last thing there, that the second, like, wavelength, because wouldn't where it says crest and amplitude, wouldn't those technically be, like, the same, like, height?
Yeah. Yeah. So I'm just showing you an example of an amplitude, but this would be an amplitude. This has an amplitude. This one has.
And the second point where you wrote amplitude, that's also a crest, right?
Yeah.
Okay.
And this would also be a trough.
Okay.
Right? Yeah. Absolutely. Good question. And then our equilibrium point or resting position would be E, this line. Anyway, guys, you guys know by now, and those that have had me last year, that drawing is not my forte at all. So sorry about that. Anyway, so for the pendulum here, okay, it's asking for the type of vibration, the amplitude, and then the total distance that the mass moves horizontally in 5 cycles. Okay, so take a look here, okay? This pendulum is moving, okay, at 90 degrees. So that should tell you the type of vibration, right? Should be transverse, okay? Now the amplitude in this case, okay, is half the distance. All right, so here's amplitude, and half of 17 is 8.5. Okay, now it says the total distance the mass travels in 5 cycles. Well, a full cycle, okay, is the pendulum moving side to side. Okay, so I'm just going to erase this for a second to show you what one cycle would look like. All right, if it starts at rest position, one cycle would be 8.5, 8.5, 8.5, 8.5, right? So in this case, okay, so rather, Okay. And so, again, if we start at rest position, okay, we're going to move through the cycle, okay, back to rest position, right? So 8.5, 8.5, but then it has to go to the right and then back 8.5, okay? So you can see here, one cycle would be 17 times 2, right? So 5 cycles, okay, would be times 10, and then we get our 170. Okay. So another thing, two waves can be identical to one another in the sense that they could have the same size amplitude, they can have the same wavelength, okay, in respect to one another, okay. However, they can also be out of phase. So a phase shift is when we actually shift an entire wave with respect to an identical wave along the x-axis. So you can see that this dotted line, this dotted wave, okay, is out of phase of the solid line, okay? And we use this concept a lot in electricity, electronics, sound, and as well the study of the atom, okay? But just all you have to know for the scope of this course is that the two waves here are identical as far as wavelength and crest and trough go, but they're being moved out of phase, rather. Okay. So time-based wave characteristics tend to be related to the motion of a vibrating particle as well as the wave. And so there are such terms such as frequency, period, and obviously the speed at which the wave travels. Okay, so we're going to go into those now as well. So frequency, as shown with a lowercase f, okay, is defined as the number of complete cycles per unit of time, okay? And we always, or normally we go based on 1 second. Okay, so time is going to be in seconds, okay? And then the number of cycles is just a number, okay? And frequency is going to be measured in hertz. Okay, so number of cycles per second would be hertz. Okay, it was named after a German scientist who first produced electromagnetic waves in his laboratory, and so they named the SI unit after him, Heinrich Hertz. Okay, so just keep in mind here that the frequency of the wave is actually exactly the same as that of the source. Okay, it is the source alone. So in this case, the hand here that is generating the vibration, the hand is the source. Okay, so once the wave is produced, the frequency actually doesn't change, and as well, its speed and wavelength do change. Okay, but the frequency never changes, and we call this behavior a characteristic of all waves. So one of the other terms that we deal with when we talk about waves, and by the way, frequency should be in your formula charts or your formula sheet, so please write that in if it's not. Okay. And as well, same with period here. So when we describe the time required for one cycle, we call that a period. And usually seconds is used for measuring a period. But sometimes when we deal with things like days and years, we're usually dealing with things like the rotation of the moon. Okay, so a period is equal to the total time divided by the number of cycles.
So on our formula sheet, there's
Yeah.
one formula that says F equals N over T, and then another one that says F equals 1 over T. Which one is the equation for frequency?
The first.
The N?
Yeah.
Not the, or the 1?
Yeah. So next to the N, you might want to put number of cycles, just so you remember. Right? Fill that in. Period is equal to, T over N, or number of cycles. Okay, so here they are here. Okay. Now, what you have as well, okay, on your formula sheet that you just mentioned, was this: frequency and period tend to be reciprocals of one another, right? So frequency is 1 over T, but T is 1 over F. Okay, so they tend to be reciprocals of one another. Okay. So here you have your two formulas. We're going to do some practice with these. Just remember that the frequency of a wave is the same as that of the source, and it is not affected by changes in speed or wavelength of the wave. So wavelength and speed do not change frequency, and you can see that by the formula, because the formula is simply number of cycles divided by time. Okay, so take a look here. We have a mass attached to the end of a spring, and it's vibrating 15 times in 12 seconds. It wants to know the frequency and the period of the vibration. Okay, so we write down we're given the number of cycles, we're given the time. Okay, so we can find the frequency. Okay, so the frequency in this case is 15 cycles divided by 12 seconds, and that will yield us with 1.2 hertz. Okay. Now for period in this case, we simply use the opposite. It's now going to be, instead of 15 divided by 12, it's 12 divided by 15. And so the period is 0.8 seconds in this case. Okay. So they are reciprocals of one another. In this question here, it says calculate the frequency of a CD player if it rotates 4.5 times 10 to the 3 times in 1 minute. Okay, so we have our cycles, 4,500 cycles, or you can leave it in scientific notation. You do have to convert your time to seconds, so 1 minute would be 60 seconds. And so to find frequency, it's just the number of cycles divided by the seconds, and we get 75 hertz. Okay, so nothing really too crazy here. This one here says if we have the moon that orbits the Earth 6 times in 163.8 days, what is its period of revolution? Okay, so here, okay, we're going to keep it in days because we're dealing with something larger here. We know that it orbits the Earth 6 times, so 6 times would be the number of cycles. We have our time in days, and so in this case, we can take our days divided by the number of cycles, and we get our period, which is 27.3 days. Okay. So that would be, in this case, 1 revolution around the Earth by the moon. Okay. Here we have 2 identical pendulums. Okay. On the left, they are said to be vibrating in phase. Okay, so this means that they have the same period and pass through the rest position at the same time. Okay. Otherwise, on the right, C and D, you can see that they too are also going to be in phase, in that they are passing through the rest position at the same time. Okay. When they are out of phase, it means that they're not passing the rest position at the same time. Okay, so both in this case, if they're passing through the rest position at the same time, they're in phase, and if they're not, they're out. Okay, so take a look here. Which pair of pendulums are vibrating in phase? Which ones are going to pass the resting position at the same time?
Is it A and D?
Okay, good. Yeah, A and D, they're in phase. Here it says, list all pairs of points that are vibrating in phase. Okay, what do you guys think? Can you list me some pairs of points that are vibrating in phase?
B and F?
B and F look great, yeah, as well as A and E. Okay, so if you take a look here, B and F are in phase, and then A and E are also in phase. Okay, nothing else is in phase. So D and H are not in phase. Okay, close, but not.
What about X and Y?
X and Y are just reference points, I believe, just for the, yeah. But even still, Y would have to be here. Okay, so as you walk, describe the movement of your arms and legs in phase or out of phase oscillations. So, you know, what I like to think about when I run is, I don't know if you ever watched the old school Mario games, or even the new school ones, where, you know, Mario jumps and, you know, it's always the opposite arm and opposite leg that move in the sky, right? Or move up, and then it's, you know, so if your right knee is moving up, it's your left arm that actually moves up. Okay, so I always think of Mario in that respect. So you can see here, if we're describing the movement of arms and legs as being in phase or out of phase, okay, if you have your left arm, okay, your left arm and your left leg are out of phase, but your left leg and right arm are in phase, and therefore your left arm and right leg are in phase, whereas the arm and the leg are going to be out of phase. Okay, so notice that when you walk, okay, if your right leg is moving forward, chances are your left arm is also swinging forward. Okay, and it reminds me of Mario when he used to do those jumps. He would always jump with the left arm out and right knee up. Okay, so there's some homework associated with this lesson, a couple of questions, 1 to 4 on 387. Okay, but we're not done yet. We're almost done. We're going to do a little bit of the next one, 8.4. Okay, and again, 8.4 is short. It's found on 388 and 391. Okay, so we covered period, frequency, wavelength. Okay, now we're going to talk a bit about speed of waves. Okay, so when a wave is generated either in a spring or a rope, okay, the wave travels one wavelength along the rope. So you can see here, if we have the source, which is the arm in this case, this rope travels one wavelength, okay, until it gets back to the equilibrium position. All right. we know that in this case that time is going to be defined as the period of the source. All right, so the time for one cycle. All right, so if you think back to the moon example, we calculated the period of the moon, which is one revolution around Earth. Okay, so the universal wave equation, okay, which in this case is v, which as we know is speed. Okay, so we know that speed is distance over time, but for sound and for waves, v is equal to the wavelength divided by the period. Okay, as well, the speed is also equal to the frequency multiplied by the wavelength. Okay, and this applies to any type of wave, whether it be sound or not. Okay, transverse, longitudinal, visible, invisible, audible, inaudible, doesn't matter. It applies to all waves. Okay, and so here it is here. Okay, so this is the one that you're going to see more of. So you have your speed, which is equal to the frequency multiplied by wavelength. And wavelength is shown by this Greek letter lambda. Okay, and wavelength is in meters as per usual, because speed is in meters per second, frequency is in hertz. Okay. All right, so you should have this on your formula sheet. It should be there. Okay. Here it says write an equation for each of the following. So if we're isolating for f in terms of v and wavelength, so basically just rearranging the equation. If you want to write these on your formula sheet so that you don't have to rearrange them on the fly to save you time, write them in. Okay, so frequency is equal to speed divided by wavelength. Wavelength is equal to speed divided by frequency. And then in terms of v and t, speed is actually equal to the period divided by the wavelength divided by the period. Okay, because remember there were two formulas. You go back, okay, right here. We're just rearranging that. Okay. Here it says the wavelength of a water wave in a ripple tank is 0.08 meters. If the frequency of the wave is 2.5 hertz, what is its speed? Okay, so we just write down our given information. We have the frequency in hertz. We have the wavelength in meters. It's simply a matter of finding speed. So we plug our information into our equation, frequency multiplied by wavelength. So 2.5 multiplied by 0.08, and we get 0.2 meters per second. Okay, so nothing too terrible here. Here, this one says the period of a sound wave from a piano is 1.2 times 10 to the negative 3 seconds. If the speed of the wave in air, okay, because remember, speed does change based on the medium that it's passing through. So the speed in air is 340 or 3.4 times 10 to the 2 meters per second. What is its wavelength? So we write down again what we have. All right. And I took them out of scientific notation, but honestly, keep them in scientific notation so that way you don't make a mistake, and just input it directly into your calculator. All right. And so wavelength in this case we know is equal to the speed multiplied by the period if we rearrange our equation. So let me just go back here. You can see the equation is equal to V equals wavelength divided by the period. Okay. So wavelength divided by period. So we just rearranged this for wavelength. So we multiplied both sides by t, right? That's all we did. That's all we're doing. Okay, so quick multiplication through the calculator, and you get 0.408 meters. This one says the distance between successive crests in a series of water waves is 4 meters, and the crests travel 9 meters in 4.5 seconds. What is the frequency of the wave? Okay, so it's giving you a bit of a clue here. It says that the distance between successive crests is 4 meters. Okay, so that tells us our wavelength. It says they do travel a distance of 9 meters, and we get 4.5 seconds for time. Okay, so we do have speed. If we take our distance and divide it by time, okay, we get 2. And that would be meters per second, which is why I have this here. So now it's just a matter of finding frequency. So we use our formula for frequency, which is our speed divided by our wavelength. Okay, so 2 divided by 4 is just 0.5, and we know frequency is measured in hertz. Okay. Some factors that can affect speed. So we know that the transfer of energy using waves is more efficient if the particle vibrations do not absorb much energy. Okay, so if you use a soccer ball as an example, okay, if you have a soccer ball that's inflated properly, okay, it's going to bounce a lot more effectively, right, than if it's flat. Okay, so even if you kick a flat soccer ball or one that's completely flat, that soccer ball is going to absorb most of the energy. But if you inflate it properly, then the transfer of energy is much more efficient. Okay, so again, if you have the atoms in the object, okay, which have strong intermolecular forces, so the bonds, so they're talking about hydrogen bonding and some other chemical intermolecular bonds, then the wave energy that we transmit is going to be more efficient. All right, and thus the wave speed is faster. So it goes back to things like a solid, which has stronger intermolecular forces. It's going to transmit that energy quicker. So that means that the wave found in a solid is much more quick. Okay, much faster. So if these forces are not strong, well, then the energy transmission is less efficient and thus slower. So you guys haven't really talked about intermolecular bonds, but intermolecular forces, these are things, these are forces between molecules. So not inside the molecule. Okay, these are forces between them. Okay, intramolecular, these are forces. These are inside the molecule. So these would be things like covalent or ionic bonds. Right? Those are examples. Whereas intermolecular means like, the molecules interacting with one another. So like a hydrogen bond for those that took chemistry. And if you didn't, don't worry. You'll know what I'm talking about later. You don't have to know it right now. So in the case of gases where the atoms are much more spaced out, you might think that cooler gases are more effective at transmitting sound than warmer gases because they're closer together, they're denser. However, we actually found that the opposite is true. We found that an increase in temperature, the molecules actually move faster, and therefore they basically bump into and vibrate with neighboring molecules much more rapidly, and therefore they transfer that kinetic energy much more efficiently. Okay, so I know that it's counterintuitive. Solids transmit this energy better than a gas because their particles are closer together. Well, a gas that is cool, that means their particles are closer together. However, warmer gas, which is the molecules are further apart, they have more kinetic energy and therefore bump into each other a lot more. So that's what that's saying. So temperature also affects the speed. Okay. If we talk about the speed of a wave along a string, such as a violin or a guitar string, okay, it's governed by a couple properties. The first thing is the linear density. So that determines how much force it actually takes to make the string vibrate. And then obviously the tension, how tense it, or, how much tension is in that string. Okay. A loose string is going to absorb more energy than a tight string. A tight string is going to transmit energy much more efficiently and effectively. Okay. So just keep in mind, these are some factors that affect speed. You should know them. Okay. It's a good multiple choice question. So temperature, right? Warm gas is going to transmit that energy much more readily, much more effectively, because the molecules seem to jostle with one another and transmit that energy a lot more efficiently. Okay. Linear density. Okay. So linear density is described as the mass of the string in this case divided by the length in meters. Okay. But you probably won't see much of this. And then we have tension in this case where we know that, in a musical instrument, they have to be tuned every now and then to make sure that there is enough tension. Or if you've ever gone bow hunting, which I can't imagine that you have, but, for hunting purposes, the bow needs to have a very tense string. And so we know that a loose string is going to absorb the energy, whereas a taut string or something that's very tight is going to transmit that energy very effectively. Okay. And we know that if we take the square root of the tension in newtons of the string and divide it by the linear density, we can get our speed. So take a look here. We have a sample problem. This is directly from your textbook. Okay, it says on your class wave machine, you have a string. It has a mass of 350 grams, which, you should convert that to kilograms. Okay. It has a length of 2.3 meters, and you would like to send a wave along this string at 50 meters per second. What must the tension be? So we're isolating for Ft in newtons. We have our two equations, and we have enough given information to find Ft. Okay. So first and foremost, okay, we've got to use our linear density. Okay, so our linear density is going to just be the mass divided by the length. So we find our linear density, which, by the way, is in kilograms per meter. Okay, why am I pointing that out? Because it will make sense momentarily. Then we can use our equation for speed, which is equal to the square root of our force of tension divided by the linear density. And we have to rearrange that for tension. Now, how do we do that? Well, if V is equal to the square root of Ft divided by our linear density, okay? Well, first of all, we have to square both sides, okay? So square both sides, and that gets rid of the square root, okay? And then if we want tension, we multiply both sides by linear density. Okay. And so that's how we get this. Okay. So we take our linear density, which is in kilograms per meter. All right. And we get our 50. We get our 50 meters, which we got from our question, 50 meters per second. Okay, which is squared in this case. And we get our tension just by simple multiplication in newtons.
Sure, like the U symbol, that was like the force of kinetic friction before.
Yeah.
It's the linear density.
Yeah.
Okay.
Yeah. So just add that to your add these to your sheet. You should have them, but add them if you don't.
Why is it the same symbol?
In physics, we kind of reuse symbols. Honestly, in Europe, they use different symbols for. In Europe, I've seen them use for initial velocity. I've seen them use U for initial velocity, right?
Okay.
Like it's different. I'm not sure the exact reasons for that, but this is the way it is. Okay. And then there's 4 homework questions, which are on page 395. Okay. So that's it for today as far as lessons go. Okay. You guys are